Shalom. This presentation is made from the website Hope and Truth. This diagram shows in the y-axis the latitude of cities where the horizontal line of 0 degree is the equator. It shows the latitude in 10 degrees increment between the two poles of the Earth. The North Pole is 90 degrees north and the South Pole is 90 degrees south. The x-axis shows the 365 days of the non-leap year. At the bottom, the days of the year are numbered in increments of 10 and correspond to the 12 months of the year shown at the top. Here are some examples of dates corresponding to the number of days shown at the bottom. 10 is the 10th day of the year, that is January 10th. 30 is the 30th day, that is January 30th. 60 is March 1st. 80 is March 21st. 170 is June 19th. 260 is September 17th, and so on. Thus we can find the day and month of the year from the day number shown at the bottom. We can see the daylight hours on curved lines from 0 to 24 hours. On the left, under January, and on the right, under December, near the winter solstice, we can see the hours of daylight vary from north to south from 1 hour to 23 hours of daylight. In the center, we see the daylight hours, which vary from 24 hours to 0 hours from 90 degrees north to 90 degrees south. The value of 0 hour here in the gray area is the constant darkness of 24 hours at the South Pole for the period indicated. In particular, I draw your attention to the 12-hour daylight curves that give the real local equinox dates for an observer located at a given latitude. For each daylight duration value and for any given latitude, this diagram enables us to obtain the approximate day of the year, that is the date, when the sun is visible during these hours. We need simply to determine the point where the daylight curve intersects the horizontal line of the given latitude. Then we can just find the day of the year on the x-axis, which is directly below that point of intersection. For example, for a city located at 10 degrees north latitude, the curve of 12 hours of daylight intersects the horizontal line of 10 degrees just before the vertical line of the 70th day, which is March 11th. Visually, the exact day can be estimated as the 67th day, or March 8th. Thus, since the curve of 12 hours indicates the real equinox, when day equals night, the actual equinox occurs around March 8 for all localities located at 10 degrees latitude north. This diagram also shows that on the line of the equator, there is never a real equinox. The curve of 12 hours of daylight never crosses the line of 0 degrees latitude. Also, when the sun crosses the equatorial plane of the Earth on March 21st, the diagram shows that there is not a single place on the planet that has an equinox on that day. Clearly, on March 21st, we find no intersection between the curve of 12 hours of daylight of equinox and any latitude. For example, at the North Pole, 90 degrees north, we can estimate that around the 78th day, that is March 19, one passes from constant night, that is 24 hours of darkness, to a constant day, that is 24 hours of daylight. Another example. For any location between 90 degrees north and 60 degrees north, the equinox curve of 12 hours is nearly a vertical line that crosses or runs along almost the same day as the aforementioned phenomenon at the North Pole, that is about March 19th. For Jerusalem, located near 32 degrees north latitude, we can estimate that the equinox curve of 12 hours crosses the horizontal line of 32 degrees north on the 76th day, that is March 17th. In fact, It is possible to know the exact times of sunrise and sunset from the website of the United States Observatory for any location on the planet for all 365 days. This is how the actual equinox dates were determined for Jerusalem from March 16 to 18, depending on the year in question. We can determine many other dates from this diagram, such as the autumnal equinoxes. In conclusion, this diagram is very useful to show the approximate local occurrence of the equinoxes versus a worldly equinox on March 2021, which in reality is not an equinox but another particular phenomenon.